Hey y'all, so we're going to be looking at this map again of downtown Austin. The first question says if 7th, 15th Street, and MLK are parallel, how could you describe the relationship between 12th and Oasis? So first, let's take a look at those streets. 7th Street is right here. 15th Street is right here. MLK is right here. So it says, take a look at these three streets. Obviously, they're parallel. But what about the relationship between 12th and Oasis? So let's look at 12th. 12th Street is right here. It looks like that's parallel with all those other streets we talked about. And Oasis is, let's see if we can find it on here. Right here. Yeah. So notice that Oasis is going a little bit more like north and south versus west and east. So this street, compared to all those ones that I highlighted in yellow, is what we call perpendicular. And that is what we're going to be talking about mostly today. The relationship between perpendicular lines. So what perpendicular means is that the two lines, let's see, they are perpendicular. The two lines intersect at a 90-degree angle. So you can see that like 12th and Oasis are intersecting at this 90-degree angle. So you would say they're perpendicular. Same thing with like west and 11th. Anytime you're going to have two lines that intersect at 90 degrees like this, even if they're kind of offset, you call them perpendicular. And so we'll talk a little bit about how those slopes are related, just like last time when we talked about parallel slopes. Let's try to answer some of these questions. Use the map provided to write the equations that can model the following streets. So we got 8 that we need to take care of here. Colorado, 6th, Lamar, 12th, Vaca, MLK, I-35, and 10th. So let's start with Colorado and 6th. So let's see, Colorado's right here, so I'm going to do that in pink. I'm going to do all these north-south-ish streets in pink. Oh, Colorado Street. Oh, that's kind of weird. For the purposes of this, let's go ahead and use this line, because look at this. It kind of curves right there. So let's just use this longer section of Colorado Street, because if this were to like continue on, you could see that like the rest of the line, or the rest of the street's right there. So we'll just sort of ignore this little section. Okay, so Colorado, we're going to have to write an equation for that one, and 6th Street. So 6th Street is down here. And those are the two equations we want to write. So it looks like both of these are going to have y-intercepts that are going to be pretty easy to identify. So Colorado, for instance, has this y-intercept of -1. 6th has a y-intercept of -2. And so let's look at the slopes of this line. So, for instance, Colorado goes up 1, 2, 3 over 1. And so the slope is going to be 3, +3 over +1. So we can write the equation for Colorado here. Y equals, the slope was 3x, and then the y-intercept was -1. For 6th Street, 6th Street has the y-intercept of -2, and it looks like the slope is going to be down 1 over 1, 2, 3. So down 1 over 3 would be -1/3. So -1/3 x minus 2. So what we'll see on all of these streets, because they're in this little grid pattern, is that just like how we looked at these yesterday, or not yesterday, but on Monday, all the ones that are kind of going north-south-ish, it is kind of crooked, but the ones that are going like up and down are going to have a slope of 3, and the ones that are going left and right are going to have a slope of -1/3. So that can help us writing the rest of the equations. We don't have to calculate those slopes every time if we take note of those and just know that they're all the same. So let's look at the next set. Lavaca versus MLK. So MLK is up here, all right? Now the y-intercept's not so obvious here, so let's pick a point. You know, it looks like it's in between these two. So let's pick a point that's a little bit more obvious, like let's say this one right here. And we're probably gonna have to write this in point slope form. That's okay. Mostly what we're gonna be paying attention to here is what the slopes or the relationships of the slopes of these lines are. So this coordinate right here, where MLK hits, is 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 9. And just make a little note here. 2, 9. And we said the slope was, you know, down 1 over 3. So negative 1/3, just like 6th Street. So we're going to write this in point slope form. Y minus 9 equals negative 1/3 times x minus 2. And again, what we're really focusing on here are the slopes, right? So anyway, negative 1/3, negative 1/3, 3. You can sort of guess that this one's going to be 3. Let's take a look at Lavaca. Where is Lavaca on here? Found it. It's right here. Looks like it's parallel to Colorado Street for the most part, if we ignore this little weird section. Lavaca goes all the way. So it's going to have a slope of 3, and this y-intercept's pretty obvious, right? It's 2. So we'll go with that. We'll use slope-intercept form for this one. So the slope is 3, y-intercept's 2, so y equals 3x plus 2. Now let's look at Lamar versus 12th. So Lamar Boulevard is, let's see, where's Lamar? There it is, over here. And it curves a little bit here. We're just going to kind of ignore that section of it and just focus in on this linear section. Okay, so there's Lamar. Y-intercept, who knows? Like it's going to be way up here above the graph, so we're going to definitely use point slope form here. A real obvious point here would be this x-intercept, right? That'd be 1, 2, 3, 4. Let's see, 1, 2, 3, 4, 5, 6, 7. Negative 8. All right, so negative 8 comma 0 is going to be the point we use for that one. And you could pick any of the other points. That would be fine. Like if you looked at this and you said, okay, well, you know, this one down here, that would be negative 9, negative 2, and that'd be okay. So the slope here is going to be up 3 over 1, just like all the rest of those. So y minus 0 equals 3 times x plus 8. Now let's identify the equation for 12th Street. So 12th Street we've already got highlighted here. It was talking about that in the very first prompt. The y-intercept here, not super obvious here, but we can use like either this point or this point, either one of these. I'm going to go with this one right here, where it intersects with Nueces. So that coordinate's negative 2, comma 4. I'm just going to make a little note so I don't forget. So negative 2 comma 4, the slope is going to be negative 1/3, as with all of those west-east streets. So y minus 4 equals negative 1/3 times x plus 2. I-35, that's the highway, that's that East Highway. That's going to be this one right here. This is going to be another one where the y-intercept is not going to be very easy to find. So we'll use point slope form. And I hope that you notice, you know, when the y-intercept's obvious, when you can just really clearly see what the number is, if it's an integer, then we're going to use slope-intercept form. But when it's not, like this one or Lamar, or even if it's going to be like somewhere in the middle like Nueces, it's easier to write it in point slope form. So this one, I'm just going to go ahead and I guess use this point right here, right where it says 35. And that one is 1, 2, 3, 4, 5, 6, 7, 8. comma negative 1. 8 comma negative 1. And I'll write my equation in point slope form. This is going to be a northwest, so the forgot the y. Y plus 1 equals 3 times x minus 8. And then let's take a quick look at 10th Street. So 10th Street, luckily the numbered streets are a lot easier to find because they go in order. So here's 10th Street right here. I'll go ahead and highlight it. So 10th Street, the y-intercept looks like it's about 1.5, but let's pick a point just to be a little safer here. So I'll pick this 1, 1. Okay, so I'm going to use 1, 1. Slope I already know is negative 1/3. Let's make a little note here. 1, 1. Y minus 1 equals negative 1/3 times x minus 1. Now I want you to take a look at how these slopes are related. Now 3 is the same thing as 3 over 1. So it looks like it's like this fraction, but flipped, but also this is positive, this is negative. And that's going to be true, that relationship is going to be true for all perpendicular lines. So let's elaborate this on this a little bit. Number 3 says, how are the pairs of streets listed above related? Well, in each pair, you have a set of perpendicular streets. Each pair is a set of perpendicular lines. And how are the slopes of the perpendicular streets related? Well, if you have a whole number, this is like 3 over 1, and then the other one that it's perpendicular to is negative 1 over 3. So there's basically two things happening here. One is one's positive and one's negative. So let's make note of that first. One is positive, the other is negative. And then the other thing that's true about these slopes is that the fraction is basically flipped, right? 3 over 1, 1 over 3. So the slope, the fraction, the rise over run, has been reversed. Okay, so the fraction is flipped. Now there's a better way to describe the relationship between these slopes. Basically you're going to have these two statements, but we can sort of say it a little bit more efficiently. We say one is positive, the other is negative. We can say that the two slopes are opposites, and when the fraction is flipped, we say they are reciprocals. So if you want to describe the slopes or the relationships or the relationship between the slopes of perpendicular lines, you say they're opposite reciprocals. Okay? So that's pretty important here. We're going to keep referring to that idea of the slopes being opposite reciprocals as we go forward. So let's knock out these last couple of questions. It says, which street can be modeled using the function negative 1/3? Okay, so we know right away that it's going to go west-east, x plus 8. So let's look and see which road has a y-intercept of 8. 1, 2, 3, 4, 5, 6, 7, 8. Right here. Let me just recount that, make sure I'm good. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, right here. And if the slope is negative 1/3, down 1 over 3, yeah, we can see that the street in question is this 17th Street. It's got a y-intercept of 8 and a slope of negative 1/3. So yeah, that would be 17th Street. And then finally, which street can be modeled using the function y plus 1 equals 3? Okay, so the slope is 3, so we know it's that north-south street. And then the coordinate it passes through is going to be 1, comma, negative 1. So let's go look for that street. 1, comma, negative 1. So 1, comma, negative 1 is right here. And the street that has a slope of 3 is Congress Avenue? It looks like it kind of skips and continues on up here. All right, so that's Congress. All right, so we've looked at sort of a real application of these perpendicular lines. Now let's take a few minutes to just sort of summarize what I want you to understand about perpendicular lines and look at it a little bit more abstractly. All right, so perpendicular lines, two lines are perpendicular if they intersect to form right angles. Lines are perpendicular if and only if their slopes are opposite reciprocals. Vertical lines and horizontal lines are always perpendicular. So here's some examples of perpendicular slopes. Let's say you had a slope of 2/5. The slope of a perpendicular line would be -5/2. Notice the fraction flipped, and one's positive, one's negative. If I have a slope like 1/3, then the perpendicular slope would be -3/1, which is just -3. -3. If I had a slope like 7/3, then the perpendicular slope would be -3/7. If I have a slope that's, say, 2, then the perpendicular slope would be -1/2. This question says, which of the following are perpendicular to y equals -3x plus 5? So what we're really looking for are lines where the slope is going to be +1/3. So we're going to put all of these into slope-intercept form. If they're not already, then you can see this one's already in that form. And try to figure out what the slope is. So this one already has a slope of 1/3. That one's good to go. Let's solve this one for y. We'll add 2x to both sides, which will give me 3y equals 2x plus 9. And then if we divide by 3, and we're dividing every term by 3, we get y equals 2/3 x plus 3. So in this case, notice that the slope is 2/3. That's not the opposite. It is opposite of this, but it's not reciprocal. So this one's not going to be perpendicular. Let's check this last one. We're going to add x to both sides to give me 3y equals x plus 6. Then when we would divide both sides by 3, I get y equals 1/3 x plus 2. So this one does have a slope of 1/3, which is the opposite reciprocal of -3. So this one's also perpendicular to y equals -3x plus 5. All right, number 2 is asking whether or not these two lines are perpendicular. And it looks like they might be, but we need to double check, okay? And to double check, we need to check to see whether the slopes are opposite reciprocals. So line A, this one right here, says passes through the points -2, 7. Wait a minute. And 1, 5? All right, well, this graph is obviously no good. I don't know what's going on here. Yeah, forget about this. So -2, 7. And 1, 5. So this would be line A. This has nothing to do with this graph over here. Just forget about this graph. And then line B goes through 4, 1 and 8, 4. So to check to see whether or not these two lines are perpendicular, the easiest way to do it is to check the slopes and see if they're opposite reciprocals. So for line A, My change in y is -2, my change in x is 3, so my slope is -2/3. So before we calculate this, what does the slope need to be perpendicular? Well, if it's the exact same, it'll be parallel, but to be perpendicular, it needs to be the opposite reciprocal. So the slope that's opposite reciprocal of -2/3 would be +3/2. So that's kind of what we're looking for. Okay, the change in y is 3. Looking good so far. The change in x is -12. So the slope here is 3 over -12, which reduces to -1/4. These are not even opposites, much less reciprocals. So these are not perpendicular. Looks like this graph might just be another problem. We could tell real quick that these are going to be perpendicular. If we check the slopes, let's go ahead and just take a quick look at it. So the slope of line A in this situation is going to be up 2/1. And then the slope of line B would be down 1/2, so -1/2. These are perpendicular. And you can see pretty obviously that they do form a right angle here. You want to be careful about just eyeballing the right angle, because even if they're like a little bit off, they might look like they're intersecting at a right angle. So you have to check the slopes every time. So yeah, these two are definitely going to be perpendicular. Not these two, though. So let's try to write some equations of perpendicular lines. So really, this is just going to be more practice from what we did in the last unit, writing equations of lines, but also taking into consideration what has to be true about the slopes of perpendicular lines. So number 4 says, write an equation in slope-intercept form. Slope-intercept form, if you recall, is y equals mx plus b, of the line that passes through -3, 1, and is perpendicular to this equation right here. Okay, so number 1, the point has to pass through -3, 1. We could plot that right away. Let's go ahead and do that. What we're going to have to do here, because we don't know what the y-intercept is, we don't know this b value, is we'll put it into point-slope form first, and then manipulate it into slope-intercept form. So we've got this x1, y1, that's the -3, 1. So I'll go ahead and start that. Y minus 1 equals, I'll leave the slope blank for a minute. I'll just leave a little line here. We'll fill in the slope in a sec. Times x minus x1. So minus -3 would change that to +3. So what's the slope? Well, if it's perpendicular to this line, then we know that the slope has to be the opposite reciprocal of this slope. So this slope is 1/2. What slope is perpendicular to 1/2? Well, -2/1. So this is the opposite reciprocal. -2/1 is the same thing as -2, so we'll fill that in right here. And there you go, there's your equation. You can definitely use the graph to kind of help you visualize this. If the slope is -2, we'll go down 2/1, just to get an eyeball check and see if these two lines actually look like they're perpendicular. So we've got this one is the line that we just wrote, right, this equation here. The one that it's supposed to be perpendicular to is this y equals 1/2 x plus 3. So that has a y-intercept of 3. The slope is 1/2, up 1/2, up 1/2. And we can finish graphing this line. Really, we just are trying to see that, yes, in fact, these do intersect at a right angle. On number 5, we're doing kind of the same thing. We want to find an equation in slope-intercept form. Again, that's y equals mx plus b. And in case you forget the forms, they're up here. So if you ever need to reference them real quick, or you can look at your star formula chart, those will be given. It passes through -3, 5. That's going to be our x1, y1. So we'll use the same sort of strategy where we start off with point-slope form, and then try to get it into slope-intercept form. -3, 5, just to kind of get a visual picture of what's going on here, is right there. So let's start this out. Y minus 5 equals something times x plus 3. So the slope here has got to be perpendicular to negative 4. So negative 4 is the same thing as negative 4 over 1. So that slope will be perpendicular to 1 over 4, positive 1 over 4. So we know the slope is this. So in both of these cases, we've got them in point-slope form. We haven't yet put them into slope-intercept form. And I just wanted to do those kind of at the same time, back to back, so you could kind of get a better feel for how to do that. We've done this a lot in the last unit, so this will be a little bit of a review. But in both these cases, you want to start by distributing the slope. Okay, and then in number 4, that gives me y minus 1 equals negative 2x minus 6. And in number 5, that gives me y minus 5 equals 1/4 x plus 3/4. The last thing that you need to do is move this constant over. So I'm going to add 1 here to both sides. That'll give me y equals negative 2x minus 5. And you can see that the fact that we got negative 5 as a y-intercept should look right with the graph that we made, right? 1, 2, 3, 4, 5. And to finish off number 5, we're going to add 5 to both sides. Now this 3/4 plus 5 is going to be like 5.75. You can write it as a decimal if you want, or if you just want to be really careful with the fractions, don't be afraid to use the calculator here. Let's clear all that out. Alpha y equals, I'm going to do 3/4, oops, oh boy. So 3/4 plus 5, and I get 23/4. So that is 5.75. Let's just look real quick to see that these are in fact perpendicular. The graph of this equation we just plotted, right, passes through negative 3, 5, and is perpendicular to this line, so the slope's going to be 1 over 4, 1 over 4, up 1 over 4. And so we get this line right here. You can kind of see, let's see, 1, 2, 3, 4, 5.75, that looks about right as far as the y-intercept's concerned. The line it's supposed to be perpendicular to is negative 4x minus 1. Y-intercept's negative 1. Go down 4 over 1. Continue that pattern backwards. And you can see, just like with the last case, these do appear to be, in fact, perpendicular. They intersect at a right angle. The very last thing we're going to do here is to identify whether or not these lines are parallel or perpendicular. So remember, if they're parallel, they have the same slope. And if they're perpendicular, the slopes are opposite reciprocals. So what we want to do here is try to find the slope of all these lines. And to do that, I think the easiest thing to do, like we did before, is just to put it into y equals mx plus b form, and then just call out the slope. What is that m value? So like 6a is 4, right? Slope's 4. We don't really have to do anything. It's already in slope-intercept form. For b, we're going to move the x over and then divide by 4. So we're going to subtract x on both sides, which would give us negative x plus 4, and then divide everything by 4. So this is negative 1 over 4x plus 4 divided by 4 is 1. So the slope here is going to be negative 1/4. And then for this one, we need to add the 2x over to the right side and then divide by negative 8. So we're going to add 2x to both sides to give us negative 8y equals 2x minus 16. And then when we divide by negative 8, that gives me y equals negative 1/4 x plus 2. So this slope is also negative 1/4. So we can see that b and c are going to be parallel. They have the same slope, and they are the opposite reciprocal of this one, right? 4 is the same thing as positive 4 over 1. So we can say that for question 6, A is perpendicular to B and C, And we can also say B is parallel to C. For number 7, it looks like the only one that's ready to go here is B. This slope is 3. For A, we need to subtract 2x, and then divide everything by 6th, and we get negative 1/3 x minus 1/2. So the slope here is negative 1/3, which is going to be perpendicular to B. So I'm going to make a note of that. A is perpendicular to B. And let's see what's going on with C here, see if that has anything to do with the other two. We're going to subtract 18x, and then divide by negative 6. It should be 3x minus 9/6 would reduce to 3/2. Don't really care what this is to answer this question. What we really want to know is what's the slope, and the slope here is 3. So A is perpendicular to B. It's also perpendicular to C, so kind of the same answer as the last one. B and C are going to be parallel because they have the same slope. So that's about it. Really, your big takeaways from today would be that if lines are parallel, then they have the same slope. Okay, but if they're perpendicular, the slopes are opposites, but also reciprocal. So one's positive, one's negative. So they're opposites, meaning one's positive, one's negative, but they're also reciprocals. So you flip the fraction. Parallel lines are lines that don't intersect ever. Perpendicular lines are intersect at a 90-degree angle measure. So over the last 2 days, this is really what we're focusing on, and just really keep in mind the relationships of the slopes.